Welcome to today's paper reading. Today's paper is titled, Projecting Points to Axes, Oriented Object Detection via Point Axis Representation. This paper was published on AR14 by Zeyang Zhao and colleagues from the Institute of Artificial Intelligence and Robotics at Ziyang University. The point axis representation for oriented object detection, as introduced in this paper, is designed to enhance the flexibility and geometric intuitiveness of object detection in aerial images. This representation is composed of two main components, points and axes. Points are used to delineate the spatial extent and contours of objects, providing detailed descriptions of their shapes. Axes, on the other hand, define the primary directionalities of objects, offering essential orientation cues that are crucial for precise detection. A significant advantage of this representation is its ability to decouple location and rotation, which addresses the loss discontinuity issues commonly found in traditional bounding box-based approaches. This decoupling enhances the precision of object detection, making the point axis representation a powerful tool for aerial image analysis. Figure 1 showcases robust oriented object detection results using the point axis representation. This representation is particularly effective in aerial images, where it emphasizes flexibility and geometric intuitiveness. The key components of this representation are points and axes. Points are used to delineate the spatial extent and contours of objects, providing detailed shape descriptions. Axes, on the other hand, define the primary directionalities of objects, offering essential orientation cues crucial for precise detection. This approach decouples location and rotation, addressing the loss discontinuity issues commonly encountered in traditional bounding box-based methods. The point axis representation is integral to the oriented DTR model, which integrates the DTR framework for precise point axis prediction and end-to-end detection. Experimental results have demonstrated significant performance improvements in oriented object detection tasks. Oriented object detection is a critical task, particularly in aerial images where objects are often not aligned with the image axis. This introduces significant challenges due to the need to account for rotation. The point axis representation is a novel approach proposed by the authors as an alternative to traditional bounding box methods. This representation is designed to more accurately capture the orientation of objects, thereby improving detection accuracy. Additionally, the use of detection transformers in this context enhances the feature extraction process, leading to better overall detection performance. Figure 2 illustrates the three main approaches to representing oriented objects. The first, A, uses a rotated bounding box, which faces issues with loss discontinuity due to abrupt changes in rotation. The second, B, employs a point set representation, which excels in capturing detailed locations but lacks orientation cues. The third, C, our proposed point axis representation, effectively separates location and rotation, providing a more flexible and continuous modeling approach. This method also includes axes for orientation cues, addressing the limitations of the other two methods and leading to more robust optimization and consistent prediction in oriented object detection tasks. Oriented object detection is a crucial task in computer vision, requiring a flexible and accurate approach to handle objects that are not aligned with the image's axis. Unlike traditional object detection methods, which use horizontal bounding boxes, oriented object detection employs rotated bounding boxes. However, current methods face challenges such as loss discontinuity and ambiguous definitions, particularly when dealing with objects that have similar long and short edge lengths. To address these issues, the authors introduce a novel point axis representation that uses points to describe object shapes and axes to provide orientation cues, offering a more robust and continuous modeling approach. In the field of oriented object detection, previous methods have primarily focused on rotated bounding boxes, which have faced challenges such as boundary issues due to the periodicity of angles. Point-based methods have also been introduced but struggle with accurately describing both position and orientation. In contrast, our point axis representation decouples these aspects, providing a more effective solution. Regarding detection transformers, the DTR framework has been adapted for oriented object detection, but these adaptations often neglect the alignment issues with image axes and suffer from the same representation problems. Our study integrates the point axis representation with the DTR framework to address these shortcomings. Figure 3 illustrates the overall framework of the point axis representation. Part A visually depicts the representation method, showing how each oriented object is defined by a set of points and an axis representation. Part B outlines the overall process of loss constraints, detailing how the model is supervised to optimize its predictions. Part C introduces the key loss, max projection loss, which is designed to supervise the point set learning by encouraging the model to learn the optimal set of points that best represent the shape and contours of the object. This loss function focuses on the projection of points onto the object's boundary, helping the model converge toward a more accurate representation of the object's spatial extent. The point axis representation in oriented DTR is a novel approach to defining oriented objects. Each object is characterized by a set of points pi and an axis representation AI. The points include k points, with the kth point serving as the object's center. The axis representation uses Gaussian smoothing to encode directional information. This method offers several advantages, such as decoupling orientation from the bounding box to prevent abrupt changes at boundaries, and using circular labels to maintain angle consistency. The representation is further enhanced by two specialized loss functions, max projection loss and cross-axis loss, which ensure effective model optimization. Figure 4 illustrates the architecture of oriented DTR, a model designed for object detection tasks. The architecture begins with an input image, which is processed by a backbone to extract features. These features are then enriched with global context through a transformer encoder. The model selects the top-end features as object queries, which are converted into k-point queries using an object-to-point query conversion function. These point queries interact through a points detection decoder, which includes point-to-point and object-to-object attention mechanisms. Finally, a prediction head generates the output based on these interactions. The experiments were conducted on three main datasets: DOTA, DOR, and HRSC 2016. DOTA consists of 2,806 images with 188,282 instances. DOR has 23,463 images with 190,288 instances, and HRSC 2016 includes 1,061 images. For implementation, the model was trained for 36 epochs on DOTA, DOR, and COCO datasets, and 50 epochs on HRSC 2016. The Atom W optimizer was used with an initial learning rate of 0.0001 and a weight decay of 0.0001. Training was performed on 4 RTX 4090 GPUs with a total batch size of 8. The ablation study focused on 3 key components: axis representation learning, the number of points representing each object, and point loss constraints. Figure 5 illustrates the distributions of predicted axes for objects that lack a clear orientation definition. This visualization helps to understand how the model handles objects with ambiguous directional characteristics, such as certain swimming pools. Despite the inherent ambiguity in the annotations of such objects, the model is able to learn and predict directional information, covering all possible directions through the distributions. This demonstrates the robustness of the model in dealing with objects of varying directional clarity, and its capability to provide meaningful predictions even in the presence of annotation ambiguities. Figure 6 illustrates the impact of varying the number of points k on model performance. Quantitatively, increasing k from 5 to 13 resulted in a modest improvement of 0.49% for map 50 and 0.5% for map 75. Visually, more points facilitate more precise localization. Even with just 4 boundary descriptor points at k equals 5, the model can accurately predict rotated bounding boxes, largely due to the auxiliary axis predictions. Figure 7 presents the visualization of results from oriented DTR in the DOTA dataset. The figure demonstrates that oriented DTR, using both ResNet 50 and SwinT as backbones, achieved map 50 scores of 79.1% and 79.8% respectively, surpassing all previous methods. Notably, oriented DTR showed significant performance gains over other DTR-based methods, such as EMO2 DTR, ARS-DTR, and AO2 DTR, with increases of 7.5%, 4.3%, and 1.4% respectively. This visualization underscores the superior performance of oriented DTR in object detection tasks within the DOTA dataset. Table 1 presents a performance comparison of our model with different numbers of points representing each object. The analysis shows that increasing the number of points from 5 to 13 resulted in a modest improvement in performance metrics. Specifically, the mean average precision at 50% IOU, map 50, increased by 0.49%, and the map at 75% IOU, map 75, increased by 0.5%. Despite this, even with only 4 boundary descriptor points at k equals 5, the model was able to accurately translate predictions into rotated bounding boxes, largely due to the auxiliary axis predictions. This table highlights the model's ability to handle varying numbers of points and still provide meaningful and precise localization results. Table 2 presents a performance comparison under different point constraints. It highlights the map 50 and map 75 values for loss max projection and various max projection variants, including those with penalties and top K constraints. Notably, the table shows a significant drop in accuracy when K equals 2, suggesting that excessive constraints may negatively impact the flexibility and optimization of point set representations. Table 3 presents the results of an ablation study on the design of the points detection decoder. The baseline, derived from a two-stage deformable DTR, achieves a map 50 of 72.8% and a map 75 of 45.25%. Introducing group self-attention improves these metrics by 1.82% and 1.19% respectively, addressing ambiguity in point query interactions. Further enhancement comes from decoupling cross-attention modules, which leads to an additional increase of 2.55% in map 50 and 4.89% in map 75, demonstrating the effectiveness of specialized feature learning. Table 4 presents a comprehensive comparison of oriented DTR with state-of-the-art methods on the DOTA dataset under a single-scale training and testing protocol. The table highlights that oriented DTR, utilizing ResNet 50 and SWIN-T as backbones, achieves map 50 scores of 79.1% and 79.8% respectively, surpassing all previous methods. Notably, with the same backbone, oriented DTR outperforms the point-based representation method-oriented rep points by 2.2%. This performance improvement is further emphasized by the comparison with end-to-end DTR-based methods, where oriented DTR shows significant gains over EMO2 DTR, ARS-DTR, and AO2 DTR by 7.5%, 4.3%, and 1.4% respectively. The results underscore the effectiveness of oriented DTR in object detection tasks, particularly in scenarios requiring high precision and recall. Table 5 presents a comprehensive comparison of oriented DTR with state-of-the-art methods on the DOTA dataset. Key highlights include oriented DTR achieving a map 50 of 82.26% using the SWIN-L backbone, which surpasses the previous leading method, LSKNet, by 0.41%. Additionally, oriented DTR outperforms the best DTR-based method, AO2 DTR, by a significant margin of 3.04%. These results underscore the superior performance of oriented DTR in object detection tasks, particularly in scenarios requiring multi-scale training and testing protocols. Table 6 presents the performance comparisons of various methods on the DOR dataset. Notably, using the SWIN-T backbone, oriented DTR achieves a mean average precision at 50% intersection over union, map 50, of 74.26%, which is 3.21% higher than the previous best method. Similarly, with the ResNet 50 backbone, oriented DTR attains a map 50 of 66.8%, outperforming the best method with the same backbone by 2.89%. These results highlight the effectiveness of oriented DTR in handling the diverse targets present in the DOR dataset. Table 7 presents a comprehensive comparison of various methods on the HRSC 2016 dataset, highlighting the performance of oriented DTR. The table shows that oriented DTR achieves the highest accuracy of 98.02% under the Pascal VOC 2007 metrics, demonstrating its superior performance. Additionally, it secures the second-best accuracy of 90.56% under the Pascal VOC 2012 metrics, slightly behind the leading method. This performance underscores the effectiveness and generalization capability of oriented DTR, especially in scenarios where objects exhibit large aspect ratios and simple shapes, minimizing boundary issues. Table 8 presents the experimental results on the COCO validation set, demonstrating that oriented DTR maintains a precision advantage over baseline methods. The metrics AP, AP50, and AP75 highlight the model's superior performance in object detection tasks. Specifically, oriented DTR achieves higher AP values compared to DTR, deformable DTR, and other baseline models. The results indicate that oriented DTR is effective in general object detection tasks, even when extended to output horizontal detection boxes. Future research could focus on combining oriented DTR with more advanced training strategies to further improve its performance and versatility. The paper introduces the point axis representation, which is designed to provide a stable method for aerial-oriented object detection. This representation separates location and orientation information, and is supported by point axis loss functions that supervise both the point set and the axis without requiring additional annotations. The oriented DTR model, which leverages this representation, integrates the DTR framework to achieve precise point axis prediction and end-to-end detection, demonstrating significant improvements in aerial-oriented object detection tasks. The authors plan to extend this representation to detect arbitrary polygonal bounding boxes in the future, and will make the code publicly available to support easy reproduction of their results. Thank you for watching.